The weak nuclear force is one of the four fundamental forces in physics. You're probably pretty familiar with the gravitational force and the electromagnetic force. The weak force, however, is mostly just sort of hand-waved at and described, at least in school physics, as being that force which is responsible for decay. The aim of this video then is to pique your interest by unpacking some of what the weak force does in an easy, bite-sized way to understand. One of the greats in physics, one Enrico Fermi, in around 1933 postulated this force. At the time he was interested in what is going on in what was known as beta decay, and the force became known as the Fermi interaction, although very quickly it became known as the weak force because, well, it describes the force so well. Of the four interactions described in the standard model of physics, the weak interaction is the only one that seems to be able to change one type of fundamental particle into another. This goes by the marvellous name of a change of flavour, and flavour changing then is when one quark can change its type or transmute from, say, an up quark into a down quark. The standard model of physics suggests that each of the four interactions results from the exchange of force carrier particles. In the 1960s, these particles' properties for the weak force were predicted, and they became known as the W and Z bosons. When these particles were discovered, it turned out that one of my lecturers at university was on the team that made the discovery, so I got to hear it from the horse's mouth, which, as you can imagine, was dead cool. The W and Z particles, the exchange particles for the weak force, turn out to be really quite massive particles, and this would suggest that the weak force would have a very short range, which in fact it does. Remember that the diameter of a proton, more or less, roughly speaking, is about a femtometer, 1 × 10⁻15, while the weak force has a range of about 0.1% of a femtometer, i.e. 1 × 10⁻18 meters. So it really is a pretty short range force. We're going to take a look now at 3 examples of decays that are brought about through the weak interaction. In beta minus decay, a neutron is transmuted into a proton by the decay of a d quark into a u quark. This is mediated, or to put it another way, the exchange particle is the W minus boson, and in the process an electron and an anti-electron neutrino are released. In a similar way, in beta plus decay, a proton is changed into a neutron, and this is caused by an up quark being transmuted into a down quark, again via the weak interaction, and more specifically the W plus boson. In the process, a positron and an electron neutrino are also released. It's no exaggeration to say that if the weak interaction couldn't produce this flavour changing, then the process of nuclear fusion would not be able to happen in stars, meaning that the universe would not be stable. In other words, it wouldn't be here. We glibly talk about this process of nuclear fusion as being the combining of two protons or hydrogen nuclei within the hot, dense parts of a star. This combination or combining of the two protons leads to the formation of a helium-2 nucleus. This nucleus of helium contains only 2 protons and is therefore unstable. Because of this, one of them will undergo a form of beta decay initiated by the weak interaction, leaving us with a much more stable deuterium nucleus. The process can now continue with the addition of, yes, you guessed, another proton. Another decay process for which the weak interaction is responsible is that of electron capture. Under the right conditions, it is possible for an electron to be captured by its parent nucleus. In this case, a quark within a proton will be transmuted such that the proton becomes a neutron and releases a neutrino in the process. But it's not just hadrons that experience the weak interaction. It is in fact experienced by all particles, for example leptons too. And this suggests that some leptons, muon for example, are able to transmute because of the weak force. As always, our explanation has been relatively free of maths and of course somewhat simplified.